So, okay students, so today we have concluded our discussions on igneous petrology as such, and today we start with an understanding of sedimentary rocks. Now, sedimentary rocks are important for a very, very important reason. It supplies 98 to 99% of the total oil production of the world. So sedimentary rocks are really, really important for our sustenance and for the money, for our living, for all the wars that are fought in recent years. It's in high demand. People use oil as a global power. America, for example, has tremendous amount of oil, but it caps all its oil. It does not allow either import or export, and does not use it. They keep it for emergency. There have been major expeditions, and they have found tremendous amount of oil preserved in them, but they don't sell it and they don't use it. They buy the oil mostly from the Far East and from North American offshore rigs, from where they import the oil, because they know the importance of the oil. So oil shell, gas-fed methane, these are all in great demand. And for that, we need to study sedimentary rocks as well, because as I said, most of the oil is restricted. Almost all the oil, 99% and more of the oil comes from sedimentary rocks. There's a little bit of oil that also comes from igneous rocks, plutonic igneous rocks, but those are very small contribution to the total oil production and consumption of oil. So we talk of sedimentary rocks. Now, we have talked about plate tectonics. We also know subduction zones. We know ocean basins. We know a little bit of the continental areas. So because of these tectonic processes, there is a lot of undulation on the Earth's surface. So you have on one side, we have the Challenger Deep or the Mariana Trench. And on the other hand, you have the Mount Everest, which is about, so if you take the top of the Mount Everest and the Challenger Deep, the total distance is about 11 kilometers or more. So that's the relief difference that you generate on the Earth's surface because of this major tectonic processes. Now, sedimentary rocks. I will talk to you about sedimentary rocks. They occur on the Earth's surface. It covers 73% of the Earth's surface. That means including continental areas, including oceanic areas, they cover 73% of the Earth's surface. But they also contribute less than 8% of the total volume of the crust. So they contribute 8% or less to the total volume of rocks on the Earth's crust. That means if you put two together, it means the sedimentary rocks form a thin veneer on the Earth's surface at the interface between the Earth and the atmosphere. So it is this thin layer which spreads 73% on the Earth's surface, occupies only 8% of the total volume of the continental crust, and so you have a very thin veneer. The average width, if you calculate back, the average width of thickness of sedimentary rock is 1800 meters on continental surfaces. 1800 meters, only 1.8 kilometers, whereas your crustal depth roughly is about 30, varies generally of a stable, tectonically stable crust, varies up to 32 to 35 kilometers. So it forms only a very, very thin smear on the Earth's surface. but it is important, very important for our sustenance and life and power and consumption and all the wars that go on, the war of Afghanistan, the war of Central Asia, the war of the Middle East, is all because of oil. Today, India, Australia, South Korea, they are all part of an axis. Suddenly, why did they become friends? After a long time, they have become very good friends. They are strange bedfellows. They never saw eye to eye. New Zealand never liked India, but now today they are friends. They are also friends with America, so they will have a military exercise very soon with their navies. Why? Gasped methane. They are looking, they are trying to stop it, they are trying to protect the oil bearing zone. All this talk about free navigation, etc. is okay, it's fine. But the truth is what lies below it, the oil. And China, on the other hand, would like to do just the opposite. So it has its own friends or people it wants to occupy. One is Taiwan, for example. It wants to be close to the sea. Not because it wants to win over Taiwan just for the heck of it. No. Today's superpowers are very intelligent. They know a war should be avoided. So they don't want war. They want power over the seas. So today we start sedimentary talks. Now, my time, of course, is extremely limited, and I cannot give a detailed discussion, nor am I competent enough to give a detailed discussion. So I take it here to you a diagram, which essentially I told you is a relief difference. Most of the sedimentary rocks, I'm not saying all of the sedimentary rocks, are formed when broken pieces of different sizes are brought from higher altitudes to lower levels by the action of water, by the action of ice, which is glaciers. Also, wind also contributes to the transport of the material, so materials are distributed. And then, of course, we have some minor components which we will discuss as we move on. But essentially what is important is this diagram, you know, my prowess in drawing things is horribly bad. You know this. I don't have to tell you. I don't have to make an excuse. This was drawn by my student for you. So, it's not my drawing. What it shows is quite a bit. You have the high hills onto the left, and you have, as you move down the slope of the hills, you have the flat-lying areas, and then as you move further to the right of this, you have the water level, sea area, where you can see the rock surface. The sea is not shown here. The rock surface, for example, has a slope like this and goes down. Now, sediments are deposited everywhere. You find sediments that are formed in different ways. They are spread everywhere. Remember, they occupy 73% of the crust and 8% by volume of the continental crust. Thickness 1.8 meters, average thickness. So they form a small vineyard. They occur everywhere. Right in the mountains, in the Himalayas, for example, down to the Bay of Bengal. This would be Bay of Bengal somewhere, and this would be the Himalayas. Now, there are different types of sediments that form, just to give you an overview. And say, for example, on the hill ranges, you have the valleys, which are shown here along the valleys. So you have the rivers with their small tributaries joining in, because the slopes are very high. So there's only small tributary which go down straight down, and you have tributaries, and some of these tributaries bring in materials and they spread out on the surface. So these are called alluvial fans. These are called alluvial fans. And again, in the mountains, sometimes you have these glacier valleys where you have glaciers, and these glaciers at the tip of it, while they travel, ice melts and the water adds to it, like the Ganga and Jamuna and the Brahmaputra, they all rise in the Himalayas and flows down. And so these are the rivers that are generated. These rivers find their way through the hills and come into here. So you have glacial sediments, and then you have alluvial sediments, and then as it goes down onto the plain, what happens is, you see, on the hills you have a slope, and on the plains the slope is gentler. So what happens? The velocity of the river is very fast as it moves down gradient, but as it reaches the plain, the speed drops suddenly. So say, for example, if any of you have visited Rishikesh or Lachmanjola, for example, Rishikesh, for example, the water is simply powering its way through. But if you go to Lachmanjola, it's not like that. It's much slow rivers because the gradient is small. That's about it. So here when the river comes, then it's, it's on a flat slope. And so it will always try to find an easier way of going down. And so the river trajectories in the hills are very straight. But the river trajectory in the plains, these are much more curved and tortuous, and the term that is used is called meandering rivers. So they are not straight trajectories like in the hills. They go straight down between the valleys. It's not like that. They go in a tortuous way, and when they reach the sea, which is almost flat ground, then you have this type of a situation where a river distributes itself. These are called distributaries. In Bay of Bengal, for example, if you go further south, you will see the famous Gangetic Delta with its mangrove forests and all that. And you have the distributaries. One is when the river starts, you have what is called the tributaries. This is the direction. You see, this is the acute angle. This acute angle faces downstream. Okay, and these are the distributaries where the acute angle faces upstream. This river is flowing this way, right? So the acute angle of this river faces upstream. Here, the acute angle between the distributary and the river is downstream. That's how you distinguish a tributary and a distributary. So here, the main river distributes itself, and it produces some sort of it's fan-like thing. It has the shape of, as she has drawn, has the shape of what is called a delta. So we have the Gangetic Delta, and you can have several deltas that can also merge, right? And then the main river flows, and the main river and the distributaries flow into the sea. But as it flows into the sea is also not as simple as it looks from the top. You just see the water, you don't see what's happening downstairs. It's not very simple. First you have, when the land finishes, first you have an intertidal zone. So what is intertidal? Say, for example, if this is a plain, and this is the water level, this is the difference in the water level. This is called the high tide level, and this is the low tide. So between that, this is called intertidal. This is called an intertidal zone, where during the high tide, the water level reaches to higher level, and when you have the low tide, the water recedes back. So those who live near the sea must be very conversant with it. Those who don't live near the sea, you better go to a beach and have a look at it. Say, for example, there is a beach here in the Digha beach, so where during the high tide, you will see the water level almost coming up to the beginning of the beach. So most of the beach is covered with water, and then the water recedes. And you get about 200, 300 meters. No, not 200, not 300 meters, maximum 100, 150 meters of the beach where the water recedes to the low tide level. That is where you have the intertidal zone between the high tide and the low tide. So you can imagine here, if you have a steep plain, then the intertidal zone is this. But if you have a gentle plain, then you can see the intertidal zone is much, much bigger. Have you understood? So if you have a gentle beach, then from the high tide to the low tide, the water recedes over great length. Here we have a beach called the Chadipur beach, which if you visit, you will not be able to see the sea at all, because it had receded so far away that even if you keep walking for several kilometers, you won't be able to see. Have you been to the Chadipur beach? And how much is the intertidal zone?
Huge. Like we can just go on walking for stretches, almost a kilometer or so, or perhaps.
Yeah, that's what you walk kilometers and you don't even see the sea. You just walk on the beach. That's because the Chandipur beach is very, very shallow. But if you go to the Digha beach, for example, it will be about the intertidal zone would be about 100 meters or 150 meters. If you go to the Gopalpur beach, for example, the intertidal zone is tens of feet because it's very steep. What is very steep? The ground is very steep. So, depending upon the slope of the ground, this zone, which is called, you can see, is called the tidal zone. This is where is what is called the tidal zone. So, this you have, as I said, this is the deltide zone, this is the intertidal zone, and sometimes what happens, normally every year for the last 4 years, I've been taking students to the Digha beach for them to learn a little bit about how sediments are deposited, how waves act on it. We take also some of our younger faculty members with us who are specialists in this. So they show you sedimentary structures, different things. They used to dig trenches and show you the different structures. But this year, of course, we can't do it. So you have to entirely believe me. Sometimes what happens is, say if you have a water front, sometimes it happens that the water movement is in this direction. So if it is in this direction, one movement, it can be split into one and the other movement. One is normal to the beach, the other one is parallel to the beach. So you have got what is called longshore and offshore currents. So this current, if it is there, then it drags the sand away this way, if this is the dominant factor. If this is the dominant factor, of course, the sand is not drawn alongside. So what happens when the sand is moved this way, you sometimes create a sandy bar. Say the ocean was like this, you create a sandy bar which splits the ocean into fragments. So this is type of material that happens. This is part of the seawater which has become now enclosed because of the beach, whereas the sea is here. Say for example the Chilka lake that you have in close by, for example, is a classic lagoonal lake which is not connected to the sea directly but only through some channels, or if there are high water waves that the sea waves come and the sea water comes and falls into the lagoon. It's salty water. But then you have the part of the sea sometimes gets separated from a fragmental sea that is caught inland, because these are called spits and bars, and they separate the lagoons from the main sea. And this is because mostly of this longshore currents which drag the sand away in a particular direction and ultimately cuts off the main sea and the sea inside. So this commonly is called a lagoonal deposits. So you have lagoonal deposits, you have deltide deposits, you also have tidal flat deposits, and then as you go towards the sea, first you have if you draw the sea, for example, first you have the continents, then you have a slope like this, and then finally like this, and this is the mean water level, and so this is the high tide and this is the low tide. So you have the tidal flat, and this one here and this one here, and this one here. Here you can see this part, where the slope is like this, this is called the continental margin or the continental slope here, and then continental margin, and then you have a slope, which is this one, where you have the continental slope, and then you have the flat ocean here, where you have what is called the abyssal plain. The abyssal plain, the continental slope, and the continental margin. And here you have a continental shelf. It's also continental. So you have the continental shelf, the continental margin, which is this one. So the continental shelf, the continental margin, and the continental slope, and the abyssal plain. So these are the distances. So if you go to the internet and look for ocean floor and click on the images, you will see brilliant images that shows you tremendous variations in all this type of things. Then there is something called the reefs, like the Great Australian Coral Reef, for example. They occur somewhere in these parts. So you have this part of the sediment is called the marine sediment. It's the part that is involved in the marine environment. And these are parts of non-marine or continental sediments, where you have these types of sediments. So you can have in the hills, you can have deposits, say for example, here for example, if you go to the slope, if you go to the flat plains, like for example when the Ganges comes down from the Rishikesh, Lakshmajula and Uttar Pradesh, past to Bihar and West Bengal, that is where it is coming through a flat plain. There, this thing is very, as I told you, the speed decreases because the gradient decreases and the river has a more tortuous journey. We'll go into those later on. But so then you have this type of sediments, and along the rivers you have also sediments deposited on either side. These are the sediments that are shown. These are called fluvial sediments. These are called fluvial sediments. Then there are lakes. Sometimes, remember, she has drawn, or in the diagram the lake was drawn in the slopes. Sometimes you will have lakes in the hills. So those are called lacustrine. Lake comes from the word lacus. So lacus is the Latin name, which is called the lacustrines. Lacustrine. So you have the lacustrine deposits. And sometimes then you have another thing that I wanted to show you here. These are called evaporite deposits. Now, see it in dry climate. Say sometimes what happens. I don't know how many of you live in the villages. Those who live in towns, they're almost, I think, they know very little about what goes on around them, except for buses and cars and trucks, everything. But those who live outside the city, who are, I consider, a little more social with nature, because they have to deal with nature a bit, so they understand nature a bit. You will see that you have a pond near your village. All villages, there is a pond. There cannot be the humankind without water. It is not possible. So civilization started either along a river, like Indus Valley civilization, for example, or for example, within the Euphrates and the Tigris in Israel, or in Egypt beside the Nile. You need a fresh water source. That is the first thing you need. That is where civilization grows. So in every village there is some sort of a pond which the water is used for different purposes, sometimes several ponds. But sometimes when you have the summer, the water level goes down because there is not enough feeding of the water into the pond, and the water evaporates. So along the sides of the river you will see that they are very dried up, but also you have white materials surrounding the lake. Again, when the rain is there, then the water becomes larger and they're wiped out and they dissolve to the water. What important point that I'm going to make here is sometimes there is sin basins, for example, small basins. And during the summer months, when the heat is high, then these evaporate, and you produce all the many of the aqueous ions that are there in the solution. They have to go somewhere. So what they do is they create minerals which are deposited. We will talk more a little bit about them in the coming hour or so. But this is how evaporate sequences. They can be also lands, but remember, these are normally locked in lakes where the water, it's not connected in or out, but only during certain months. Say a river or a small river or rivulet gets in water into a depression. During the summer one, that small rivulet stops and there is no water inflow into the river system, into the pond, and the pond dries up. It's very common. So you also get evaporite sequences there. So you have different types of sedimentary rock. The last one that is important, and you should know this, and you have to read a little bit, these are called the Aeolian deposits. This is important. This essentially is shown like this, just to fit into the diagram. It's not so. It's a huge science. It's a huge, huge amount of science. Aeolian sediments are essentially wind-driven sediments. They typically involve semi-arid to arid regions. Say, for example, our third desert, for example, is a classic example. There are many, many, the Sahara, the Kalahari, some of the very famous ones in North America. These are just deserts where the sediment deposition, transport, everything depends on the movement of the wind. So the wind determines how the sand moves. So when you see a desert, you don't think the desert was there from time immemorial. That's the present position of the desert. The desert may not have been there before. Several hundred years ago, the desert had a different geometry. It has migrated because all the sand is migrating as the wind velocity is migrating. So it all depends on the weather cycle of a particular place, and that means the overall climate. So if the climate changes, then the desert movement also changes. It's very good science. So there you have, and these beautiful diagrams that she has shown, these are nothing but the very famous barkhans of the desert. These are the crescent-shaped dunes. I will give this to you for reading, but wait a bit. These are Aeolian sand. These are driven by air. This is driven by ice. And the rest of it is water-driven. Water-driven sediments, some of them are lacustrine, some of them are fluvial, some of them are marine. So you have diverse types of sediments that are being deposited on the Earth's surface, and they are being transported as the physiography of the land changes from higher altitude to lower altitude. Except that wind drives it even at the same altitude. It depends on the gradient of the wind, not on the land. Okay? And the last thing that I would like to tell you, and we will talk about this a little bit. So here you see, my student has drawn some of these fans. These are called, like the Japanese fans, they are called the fans. These are called turbidites. This is the name. Or turbidite flow deposits, or called fans or turbidite flow deposit. This is where you have the continental, you can see here you have the continental slope, and the water drives down sediments, and then suddenly you have the flat plain. So what happens? The sediments that were being carried at high speeds because of the tremendous gradient suddenly meets a flat ground, and it loses its power. And once the streams, water bodies loses its power, it deposits material. So at the top where they deposit, these are sharp edged, and as they spread out, they are like this actually. They are like this. So sometimes you have coalescent fans, continuous coalescent fans. So you will have at the continental margin, at the continental slope, and the abyssal plain, you have what is called the turbidite flow deposits, and they can merge one into the other and can form a completely different zones. Right? So this is what it is. these in this turbidite flows, as you go to the flat margin, they become thinner. So they have some sort of a wedge-shaped appearance. As they move in further away, it becomes thinner. As you're closer to the continental slope, it's much more thicker. So that's how, so it's like a wedge. If you take a transverse section, it's like a wedge. Yeah, so these are essentially the different depositional environment of sediments as very broadly, and we don't go into much of these sediments. I will only tell you a little bit about a particular type of sediments to understand, and we don't go into the great details of everything. As far as I said, I'm not competent, and second is, this is not your course. Yours is Introduction to Sedimentary Rocks. So I will just introduce to you. Those who are in geology will have large doses of sedimentary rocks in your further semester, but for me, that's it. So we go in over to the next. Now, before we go to the main, while we go to the main topic, before we go into the main topic, the classifications, etc., I will tell you, I will talk about a particular type of sediments, which we call fluvial sediments. That means, essentially, these sediments are driven by water, river water. And so I will talk about fluvial sediments. And we talk about a thing called, that means these materials are forms of where, and they are transported and they are deposited. Some of these fluvial sediments could also be deposited in situ, but most of them do not deposit in situ, and they are carried away with the movement of the water. We will talk about them. But before we do, I try and introduce two important topics that has great value to this. One is called weathering, and the other one is called erosion. These are two different terms, weathering and erosion. Now, weathering essentially involves the breakdown of a rock or a mass of rock to smaller fragments. That's how it is. Weathering involves all the processes that breaks down a larger rock into smaller fragments. And erosion is the processes, is all the processes that removes the material from the zone of weathering to a zone of deposition. Or erosion essentially involves the processes that induce transportation of the weathered material. That is what it is. So we have the two terms, weathering and erosion. Weathering involves all processes that induce breakdown of rocks from large sizes to small sizes. And this includes breakdown of hills. These are all natural processes, not humans. We can take out humans, they are stupid. So we can just take nature as it works. It's very powerful. You just saw with the coronavirus how nature can make everything into a standstill. And this brilliant earth with 8 billion people are just dumbstruck, trying to survive, cow down. Yeah, so don't consider humans as powerful at all. They're absolutely idiots. They have no value. They are part of an evolutionary cycle. So they came up to what is called the humans. Humans will evolve into something else. They are very, we are animals. So it's okay. We have some intelligent brains, so we have done great things. But you can imagine there can be more intelligent animals somewhere else. Yeah. Let's talk of nature. So all natural processes that help to break down large rocks into smaller particles. And erosion involves all the processes that transport those materials, weathered materials, from its zone of weathering to the zone of deposition, where it's finally deposited. So essentially, if I take a geologic section, this is the mean sea level, and this is how the ground surface looks like. So the major weathering that occurs is somewhere here, but it breaks down the rocks. Erosion dominates over a larger space until you have the deposition site, which is some sort of a depression. So here you have the hills and you have the slopes, not the continental slopes, etc. This is the general topography of a continent when it reaches the sea. This is the beach, then this is the continental slope, the continental margin, the continental, and this is the abyss. So weathering is dominant in these parts. Here also weathering occurs, but it's on a minor scale. How it occurs, I will show you. But erosion occurs in large areas from this. It essentially transports material as it happens. So we try to see how nature breaks down. You can take a hammer and break. You can take the cup in your mother's cupboard and throw it. It will break. But how does nature break? There are, and this is what we will do, what are the weathering processes? We will try to quickly get an idea of it. Weathering processes. Generally, there are three types. One, physical weathering. One is physical. The second one is chemical. And the third one is organic. Or better is to say biological. Weathering processes involve physical, chemical, and biological. Now, physical processes are normally divided. You can always devise, nature always devises its own way. It's very brilliant, you know. Nature is brilliant, many times more brilliant than Einstein. So you have different processes of weathering. One process is called thermal processes. The other one is popularly called ice wedging. Then pressure release. And the third and the fourth process is salt deposition. First, let's get to thermal weathering. Thermal weathering, ice wedging, then pressure release, salt deposition, Now you must be wondering how is it done? They are done in very, very nice ways, very, very intelligent ways. Remember, you have a hill, you have a rock near your house. I don't know whose house is it. If you go on a summer evening or in the post-afternoon and your girlfriend isn't there or your boyfriend isn't there and you have full concentration on listening to nature, and you place your ears, if you can, because your ears will burn, on the rock itself, and you will hear a weird sound. It says click, clock, click, clock, click, clock, and you don't know from where the sound is coming. The sound is coming. One way is when you hit a rock, it expands. When it expands, it tries to expand its volume. You see, it's a rock. It tries to expand its volume. And when it does that, it creates a lot of spaces between different parts of the rock or between different minerals. So what it is doing is, it is essentially splitting itself. And those sounds, that click, clock, click, clock, click, clock sound, that sound is coming because of the splitting of it. And then, post-afternoon, the rock is still hot at 4 o'clock. It's still hot at 4 o'clock. So if you, during the summer months in Bihar, for example, or in Jharkhand, even there you go at 4 o'clock. When I go to 4 o'clock and do my field work, I can't even put my finger on the rock because it's so hot unless it's in the shade. So we try to work on a shade normally because there you can take data. Sometimes it's not possible. But it's very hot. By evening, when the sun is down, it starts to cool. And you come in the night, once again without your girlfriend or your boyfriend, and you put your ears onto this, yes, and you will see click, clock, click, clock. What is it? The rock is now shrinking. It is creating shrinkage cracks. So there are two ways it's breaking up. Once during expansion and once during cooling. So where in places where the temperature goes high and also becomes very cool, like in the deserts, for example, the temperature goes up to 50 degrees, like in Bihar, for example, I was telling you, Bihar and Jharkhand, the temperature goes up to 50, 52 degrees at 2 o'clock, 1 o'clock or 2, 1:30 in the afternoon, the temperature is 50, 52 degrees centigrade. And then it starts cooling down. And you always hear this. Always. You can see the rock is breaking itself up. What it is doing, why is it, so what happens if the rock breaks down? First is, it breaks down into smaller parts. Now you imagine, before it broke down, imagine the surface area of a rock. Say for example, let's take a square. Let's take a square. And each side is R. So the surface area is 6R squared. Right? Now you divide it in 4 parts. You divide it into 4 halves. So what is each half? R by 2. So then it is R by 2 whole square is the surface area of 1 into 6. So that means R square by 4 R square. What happened? Where did I go wrong? R by 2 whole squared into 6. Oh, no, this is not 6R. Yeah. R squared, 6R squared. R by 2. I think I made a mistake somewhere. So this is 3 by 2 R squared. But I think you have, into 4. Because there are 4 cubes generated. So that means it is 12 by 2. I think I made a mistake somewhere.
So what are we trying to do?
I'm trying to find out the surface area. That what essentially you can find out, I made a mistake. Essentially what you can find out, if you have a cube with a particular surface area, here for example,
It's r squared. For
it's
one
r squared,
face.
so 6r squared is
Yes.
the surface area. But if you break it up, then
It
what?
increases.
It increases how?
So because for each cube, each small cube, another additional surface is generated.
Yeah, but what is it mathematically? So r by 2 will
So
be
like if we split the cube into two,
you split the pit into 4.
okay. So in that case, we are generating additionally 3 new surfaces for per piece.
No, but you can imagine, if I can create 4 spheres out of it, then you will have additional surfaces. There will be additional surfaces that will be created, and so you will have larger amount of surface area. So when the hill is cracking itself up, or the rock is cracking itself up because of thermal heating and cooling, heating in the day, cooling in the night, it's essentially increasing the surface area. Now you can ask me, please wait a bit, we will come to that. Yeah, but first, it's increasing the surface area. Then, for example, ice wedging. Now this of course does not happen at Kharagpur, Bihar or Jharkhand. This is ice wedging where there is ice involved. So what happens, normally if you have a rock, normally rocks have cracks. You will never see a rock which does not have a crack. Complete monolith, you don't have it. There are natural cracks in the rocks. So sometimes you have cracks in the rocks. And what happens is, when there is rain, water seeps into the cracks. Water seeps into the cracks. And when the temperature goes down, when water converts to ice, I will give you a value. That if you take 1 gram per centimeter cube, the density of ice, the density, rho of ice, is equal to approximately 0.98 grams per centimeter cube. And the volume expansion of ice is therefore 8.3%. Volume expansion of ice is 8.3%. So if you have water going down the crevices of the rocks, and then when ice sets in because of the coldness of the climate, then essentially the volume expansion for creation of ice is 8.3 because the density of ice is less. So once this water is trying to convert to acid, it simply pushes the material out as the ice is precipitated in the crevices, glues into the crevices. So once this is done, more cracks develop as there is pressure from the side. And as you have, then you have new cracks being developed. And the next cycle, there is some more water goes into this. And some more ice is produced as the temperature goes down. And that is what is happening. Why it is called ice wedging? Because most of these cracks actually are like this shape. If this is the surface, it's widest at the surface and then wedges itself inside the rock. So that is why it's called ice wedging. So you can also imagine the pressure here is maximum. So once you do this, then you produce these ice wedges itself cracks up the rocks. Then, for example, this again, as you can see, the same as the thermal situation, where it creates more surfaces in the rocks. More surfaces in the rocks. Then we come to the next topic, which is pressure release. So what happens if you have the ground surface and if you have rocks below, then as the top material gets eroded off, as materials are eroded off, then what happens? The pressure above the surface of the rock, this decreases. The pressure on the surface of the rock decreases. So because of this loss of pressure, there is volume expansion in this rock. So what happens? Because of the pressure release, the rock splits into thin sheets. These are called joint planes, into thin flat-lying sheets. So when you have these flat-lying sheets and when they are exposed, when it's like a hill, for example, then what happens? There are cracks like this. These are flat-lying cracks. What happens in these parts when the cracks become loose? These parts crack and they slide down the hill ranges and they produce debris. Similarly, here, as this debris is removed, as this layer is removed, the lower layer, like in an onion peel, the lower layer is exposed. So what happens is, what you are doing is flattening the ground. So you're raising the height here and reducing the height here. So essentially, you're making a plane out of an undulating topography. You're trying to flatten the plane. Nature somehow does not like relief. It wants to flatten everything. Absolutely everything. So materials, this is simply gravity flow. There is pressure release, so you get flat-lying planes, and these planes become loose, and they simply fall because of the gravity unstable. Only you will find some pieces standing here still, because obviously it's right at the peak, and it can't fall on either side. So what happens is, if you go to South India, for example, in many places where you have granite rocks, you will see, if you're traveling around that, they have magnificent appearances. Some of them look like elephants, some look like bullocks, and many of these hills in the top, there is a temple. Everywhere there is a temple. And normally the temple is built on this. Very stable. We would like to place our gods at higher levels. So we always choose these parts to build our temples. So the temples are never kept on the slope, obviously. They are very unstable and the rocks are very hard. So it's kept on the flat part, and the flat part is made of a rock, which is unstable but lying stably because it can't go down. So that's what it is. So this is what pressure release does. Pressure release generates rough surfaces which are flat-lying, and they follow normally the surface of this, and this material, when they go up, they fall due to gravity flow, and so the flanks are normally filled up by these debris that fall from the hills, and the hill itself becomes very well rounded. So if you go to geologic fieldwork and you're trying to approach a hill, please be careful, because these are the homes of snakes, and not too nice snakes, cobras, etc. They are very common. So always remember, this is a question of pressure release. Again, you see, surface areas of rocks are being increased. Surface areas of rocks are the total rock surface that is exposed to the atmosphere, that surface area is increasing every time you have any of these processes. Now we come to pressure release and then salt deposition. This is another feature, because most water that you see, they contain some sort of ions, dissolved ions. Now these dissolved ions, when the water becomes less and less, these dissolved ions are deposited in the crevices, the joints, the cracks, which are always there in the rocks. So during the growth of these crystals, as they grow with time, they also generate tremendous amount of pressure on the walls of those places where the crystals are growing. So this also creates a large amount of pressure exertion on the sides of the crevices and the joints, etc. And this helps to break the rock. So thermal stresses, ice wedging, or it's called frost wedging or ice wedging, or called pressure release or salt deposition, these are processes that typically break rocks. Say for example, if you have gone to the hills, you will see sometimes trees, huge trees, growing at the top of a hill or on the flanks of a hill. And they make it a magnificent feature. How did it grow? Where did the roots grow? So there must have been a seed there. So the plant is growing there and they produce their roots and the fruits become flatter and they push against the rock and they break the rock. It's very common. So sometimes in many buildings you will see the maintenance comes and takes out the smaller sapling that's growing at the crevices. Because otherwise they will break the wall. They create serious damage to the wall. So essentially what happens, what's happening during weathering, physical processes, bigger materials are broken down into smaller material. That smaller material means larger surface area. Smaller material means they can be transported faster. Common sense says that. It's easier to transport a smaller medium than a big mountain. Yeah. So, weathering, erosion becomes easier, but the most important thing is it's increasing the surface area. Okay? We will go into the chemical processes in the next video lecture. So, thank you.